Why don't you just get a math fluid AI bot to do this? I mean, that's the whole point of, I mean,
yeah, exactly.
It's hard for you, but give it to an AI.
Yeah.
For decades, physicists like Neil wrestled with the impossible, cracking the hidden dimensions buried inside string theory's mind-bending math. Einstein's ideas opened the door, but left humanity staring at equations no one could tame. Now, Neil reveals how artificial intelligence stepped in where humans failed, conquering calculations once thought unsolvable.
I worked on that, and then lots of other people in the field have, and we found that using these techniques, we can speed up a lot of computations in a really substantive way. And this actually made it possible just recently for groups to compute quark masses in string theory for the first time. So to be clear, these are not the quark mass values that we actually observe in nature. That would be awesome, but we don't see that yet. But we can say, if you just hand me some extra dimensions, whatever they may be, and then say, what would the quarks look like in that universe? Now we can actually come up with those numbers using machine learning algorithms.
Did AI just decode the tangled fabric of the cosmos? And what shocking truths about reality did it expose along the way? Join us as we uncover how AI finally solved the string theory mystery. Mathematical prison that trapped Einstein's legacy for decades. Einstein's equations were supposed to unlock the universe's deepest secrets. Instead, they became physics's most beautiful trap. When string theorists tried to use these equations to understand the extra dimensions that might exist beyond our everyday world, they hit a wall that would frustrate scientists for over 50 years. The problem wasn't that Einstein got something wrong. His equations work perfectly for describing gravity in our familiar 4 dimensions of space and time. But string theory suggests our universe might have 10 or 11 dimensions, with the extra ones curled up so small we can't see them. To make predictions about what we might observe in experiments, physicists needed to solve Einstein's equations for these hidden dimensions. That's where everything fell apart. Einstein's equations are what mathematicians call nonlinear, which sounds technical but creates a devastating practical problem. In normal math, if you find 2 solutions to an equation, you can add them together and get another valid solution. Einstein's equations don't play by those rules. Gravity responds to itself, creating more gravitational effects in an endless feedback loop. Each solution stands completely alone. This means every time physicists wanted to explore a different configuration of those extra dimensions, they had to start from scratch. No shortcuts existed. No general formulas could be written down and stored in textbooks. Each calculation became its own unique mathematical expedition into uncharted territory. The situation got worse when physicists realized just how many possible ways those extra dimensions could be arranged. String theory doesn't give just one answer for what those hidden dimensions look like. It offers roughly 500 million different possibilities. Each one might produce a different version of physics in the world we actually observe. So physicists found themselves facing an impossible task. They needed to solve equations that couldn't be solved analytically for hundreds of millions of different scenarios. The math required to handle even one case properly would fill entire research papers. Tackling all of them seemed hopeless. Universities invested in massive supercomputer clusters, the kind that fill entire buildings and consume as much electricity as small cities. Graduate students would submit their calculations and wait months for results. Sometimes the computers would crash halfway through, forcing researchers to start over. A single calculation exploring one possible arrangement of extra dimensions might take a research team years to complete. The delay created a strange situation in physics. String theory had elegant mathematical beauty and promised to unite gravity with quantum mechanics. But it couldn't make concrete predictions about the real world. Critics argued this made it more philosophy than science. Supporters countered that the theory was simply ahead of the available mathematical tools. Meanwhile, experimental physicists kept discovering new particles and phenomena that needed explaining. Dark matter, dark energy, and the precise masses of fundamental particles all begged for theoretical understanding. String theory seemed like it should provide answers, but those answers remained locked behind computational barriers that seemed insurmountable. The mathematical prison had claimed Einstein's legacy, trapping one of humanity's most promising theories in a cage of its own making. Decades passed while the equations sat unsolved, taunting physicists with secrets they couldn't quite reach. Then, artificial intelligence changed everything, and it turned computing itself upside down. What happens when machines stop following the old rules entirely? The supercomputer rebellion. Traditional supercomputers had always approached Einstein's equations like patient librarians, methodically working through each calculation step by step. These room-sized machines would churn through mathematical operations for months, consuming enough electricity to power entire neighborhoods while physicists waited anxiously for results. The process felt more like archaeology than cutting-edge science. Machine learning algorithms took a completely different approach. Instead of solving equations the traditional way, these systems learned to recognize patterns in the mathematical structures themselves. Neural networks, originally designed to identify cats in photos or translate languages, suddenly found themselves wrestling with the fundamental geometry of space-time. The transformation happened almost by accident. Researchers studying string theory had grown frustrated with the endless waiting periods imposed by conventional computing. Some began experimenting with artificial intelligence tools, not because they expected miracles, but because they had run out of other options. The initial results seemed too good to believe. Where supercomputers required months to explore a single configuration of extra dimensions, machine learning algorithms delivered answers in minutes. The speed improvement wasn't just incremental, it represented a complete revolution in computational physics. Calculations that once demanded dedicated research grants and years of planning could now be performed on ordinary laptops during coffee breaks. The key insight involved training neural networks to approximate solutions rather than calculate them exactly. Traditional computers had to work through every mathematical step with perfect precision, like following a recipe instruction by instruction. Machine learning systems learned to recognize what the final dish should look like and found shortcuts to get there faster. This approach initially made many physicists uncomfortable. Science had always prized exact solutions over approximations. The idea that an artificial intelligence system could somehow guess the right answer to Einstein's equations seemed almost like cheating. But when researchers checked the AI-generated solutions against known results, the accuracy proved remarkable. The breakthrough enabled something that had never been possible before. For the first time in string theory's history, researchers could rapidly explore thousands of different configurations for extra dimensions. Each possibility that once required a separate supercomputer project could now be investigated in an afternoon. The implications extended far beyond speed. With computational barriers removed, physicists could finally ask questions that had been impossible to pursue. They could test whether certain theoretical predictions actually held up when subjected to rigorous mathematical analysis. String theory began producing concrete numbers instead of abstract possibilities. Machine learning algorithms also discovered patterns that human researchers had missed. The AI systems could identify mathematical relationships across thousands of different dimensional configurations, spotting connections that would have taken human scientists decades to notice. These pattern recognition capabilities opened entirely new research directions. The transformation reached a milestone when research teams successfully computed quark masses within string theory frameworks. These calculations had been theoretical pipe dreams just years earlier. The results didn't match the quark masses observed in nature, but they proved the approach could work. Scientists could now ask fundamental questions about particle physics and get mathematical answers. The rebellion against traditional supercomputing had succeeded beyond anyone's expectations. What started as a desperate attempt to speed up calculations had evolved into a new way of doing theoretical physics entirely. The mathematical prison that had held Einstein's equations captive for decades finally had a key. All that speed unlocked something far more profound than faster calculations. Could machines actually create entire worlds that never existed? Cosmic calculator. Imaginary universes. The breakthrough in computational speed revealed an extraordinary capability hidden within string theory. Physicists could now use artificial intelligence to construct complete universes with different physical laws, different particle masses, and different fundamental forces. These weren't just mathematical abstractions. They were fully realized cosmic simulations that behaved according to their own internal logic. The process starts with the extra dimensions that string theory predicts. Each possible arrangement of these hidden dimensions creates a unique set of physical laws. Before machine learning, exploring even one of these configurations took months of supercomputer time. Now researchers can generate thousands of different universal blueprints and watch how matter behaves in each one. The AI systems act like cosmic architects, taking a specific dimensional configuration and calculating everything that would exist in that universe. They determine what particles would form, how heavy those particles would be, and how they would interact with each other. The results often look completely foreign compared to our reality. In some AI-generated universes, electrons weigh as much as protons. In others, the strong nuclear force becomes so weak that atomic nuclei fall apart instantly. Artificial intelligence doesn't judge whether these universes make sense. It simply calculates what the math demands and builds worlds accordingly. One of the most significant achievements came when research teams successfully computed quark masses for hypothetical universes. Quarks are the building blocks of protons and neutrons, but their masses in our universe seem almost arbitrary. String theory suggests these masses result from how the extra dimensions are shaped, but proving this required calculations that were impossible until recently. The AI-generated quark masses don't match what scientists observe in nature. This initially disappointed some researchers, but it actually represents a crucial step forward. The calculations prove the method works and show that string theory can produce concrete predictions about fundamental particles. Finding the right dimensional configuration that matches our observed reality becomes a matter of searching through possibilities rather than hoping for theoretical breakthroughs. The artificial intelligence systems can also simulate how these imaginary universes would evolve over cosmic time. Some collapse immediately because their physical laws make stable matter impossible. Others expand so rapidly that particles never get close enough to form atoms. A few develop complex chemistry that could potentially support life, though it would be nothing like Earth's biology. This capability transforms how physicists approach theoretical questions. Instead of spending years working through abstract mathematics, they can now test ideas by building simulated worlds and observing the results. The approach resembles video game development more than traditional academic research, with scientists designing virtual realities to explore cosmic possibilities. The speed of these calculations enables systematic exploration of string theory's landscape. Researchers can now map out which dimensional configurations produce stable universes, which ones create exotic particle physics, and which ones collapse into mathematical contradictions. This mapping process was impossible when each calculation required months of traditional computing. Machine learning algorithms have also discovered unexpected patterns across different universal configurations. Certain mathematical relationships appear consistently, even in universes with completely different physical laws. These patterns hint at deeper principles that might govern all possible realities, not just our own. The cosmic calculator continues expanding its capabilities. Recent advances allow the AI systems to simulate not just particle physics, but also larger structures like stars, galaxies, and black holes in these alternate universes. Each simulation provides new insights into how fundamental physics shapes cosmic evolution across different possible realities. All these simulated worlds revealed string theory's most overwhelming challenge. But what if the solution was hiding in plain sight like a trick of the eye? Billion universe problem and the optical illusion solution. String theory doesn't offer physicists a single answer about how our universe works. Instead, it presents roughly 500 million different possibilities for how the extra dimensions could be arranged. Each arrangement creates a different version of physics with its own unique properties. This enormous number of options became known as the landscape problem, and it nearly broke string theory as a scientific field. The scale of this challenge defies imagination. If a research team could analyze one possible universe configuration every second, working continuously without breaks, they would need over 15 years just to examine them all at once. With traditional supercomputing methods that required months per calculation, the task seemed completely hopeless. Critics argued this made string theory unscientific. How could physicists ever make meaningful predictions if they had to choose from hundreds of millions of possibilities? The theory seemed to predict everything and nothing at the same time. Some researchers abandoned string theory entirely, declaring it a mathematical dead end. Machine learning systems approach this overwhelming complexity differently. Instead of trying to examine every possibility individually, the artificial intelligence began looking for patterns across large groups of universe configurations. The AI systems discovered something remarkable hidden within all that chaos. Many of these billions of different geometric arrangements actually produce identical physics. Different ways of folding and shaping the extra dimensions can result in exactly the same particles, forces, and physical laws in the everyday world that humans experience. The mathematical structures might look completely different, but their observable effects remain identical. This redundancy works like an optical illusion that can be interpreted in multiple ways. A single image might appear to show either a vase or two faces in profile, depending on how the viewer focuses their attention. Both interpretations are equally valid, even though they seem to describe completely different objects. String theory's landscape contains similar mathematical illusions, where different geometric configurations are actually different perspectives on the same underlying physics. The discovery means physicists don't need to search through all 500 million possibilities after all. Large groups of configurations can be treated as equivalent, dramatically reducing the search space. Instead of examining hundreds of millions of separate cases, researchers might only need to investigate thousands or tens of thousands of truly distinct physical scenarios. Artificial intelligence systems excel at identifying these equivalences because they can rapidly compare mathematical properties across enormous datasets. The pattern recognition capabilities that allow AI to spot faces in photographs or detect fraud in financial transactions work equally well for finding hidden symmetries in theoretical physics calculations. This breakthrough transformed the landscape problem from an insurmountable obstacle into a manageable research program. Teams can now systematically explore string theory's possibilities without getting lost in mathematical redundancy. The AI systems act like guides through a vast library, pointing out which books contain the same information even when their covers look completely different. Recent advances have pushed this approach even further. Machine learning algorithms now identify not just exact equivalences, but also near equivalences where different configurations produce almost identical physics. This expanded pattern recognition reveals new mathematical relationships that human researchers had never suspected, opening additional pathways for theoretical exploration. The optical illusion solution didn't eliminate string theory's complexity, but it made that complexity navigable for the first time in the theory's history. All these mathematical shortcuts revealed something even stranger lurking in the equations. What if the most important physics in our universe is completely invisible? Hunting, invisible forces, and broken symmetries. The AI breakthrough. In string theory, calculations opened the door to investigating phenomena that had puzzled physicists for decades. Hidden within the mathematical structures were signs of forces and particles that don't interact with ordinary matter in any obvious way. These ghost-like entities leave fingerprints throughout the equations, but remain completely invisible to direct observation. Supersymmetry represents one of the most intriguing examples of this hidden physics. The theory suggests that every particle humans can observe has a massive shadow partner lurking somewhere in the universe. Electrons would be paired with selectrons, quarks with squarks, and photons with photinos. These superpartners possess the same fundamental properties as their visible counterparts, but carry much greater mass. The Large Hadron Collider spent years searching for these supersymmetric particles without finding any trace of them. Many physicists began dismissing the entire concept as mathematical fantasy. The AI-powered string theory calculations revealed why the search came up empty. The superpartners exist at energy scales far beyond what current experiments can reach. Their effects only become visible through subtle influences on the particles that scientists can actually detect. Machine learning systems excel at spotting these indirect signatures. The algorithms can analyze thousands of theoretical scenarios and identify which ones produce observable effects that match experimental data. This pattern recognition revealed that supersymmetry might be broken in our universe, meaning the symmetry between particles and their superpartners gets disrupted by other physical processes. Broken symmetries create some of the most fascinating phenomena in physics. When a perfect mathematical symmetry gets disrupted by real-world conditions, it often produces new particles or forces that wouldn't exist otherwise. The Higgs boson emerged from broken electroweak symmetry. The masses of fundamental particles result from broken gauge symmetries. String theory suggests additional broken symmetries might explain dark matter, dark energy, and other cosmic mysteries. Artificial intelligence systems can now explore how different types of symmetry breaking affect the physics that emerges from string theory. The calculations reveal that certain ways of breaking supersymmetry could produce particles that interact only through gravity. These particles would be completely invisible to electromagnetic forces, making them perfect candidates for dark matter. The ghost physics extends beyond supersymmetry. String theory predicts additional spatial dimensions that remain hidden from everyday experience. These extra dimensions might contain entire ecosystems of particles and forces that never interact with ordinary matter. The AI calculations show how these hidden sectors could influence visible physics through gravitational effects or other extremely weak interactions. Fifth forces represent another class of ghost phenomena that machine learning algorithms have helped identify. Beyond the four fundamental forces known to science, string theory allows for additional forces that operate only under specific conditions or at particular energy scales. These forces might be responsible for cosmic acceleration, the formation of large-scale structure, or other unexplained astronomical observations. The computational revolution has also revealed how quantum field fluctuations in extra dimensions can create apparent violations of known physical laws. Effects that seem to break conservation of energy, or momentum, might actually involve energy transfer into hidden dimensions that human instruments cannot detect. The AI systems can track these transfers and predict their observable consequences. Recent breakthroughs have enabled physicists to calculate how these ghost phenomena would manifest in laboratory experiments. Instead of hoping to directly create supersymmetric particles or fifth forces, researchers can now look for their indirect effects on processes that are already well understood. The AI-generated predictions provide roadmaps for designing experiments that could finally detect evidence of physics beyond the standard model. The invisible universe no longer represents pure speculation, but has become a concrete research target with specific predictions and testable consequences. What happens when AI discovers physics that even Einstein couldn't imagine? Could we be living in one of those simulated universes right now? Share your thoughts with us in the comments section. Remember to like, share, and subscribe for more. Also, click the next video showing on your screen. You will enjoy it.